Okay, so we've gone through some discussion about these different sub-object classifier and whatnot for this category of dynamical systems. Now let's see this. Well, I mean, for generally for categories of functors into sets. Now let's apply this to the case of categories of dynamical systems. So these dynamical systems are functors from this category here, which is the free monoid with one generator, called generator sigma. And so to apply the Yoneda lemma, we want, so our objects in this category are functors from this C to set, and the arrows are natural transformations between them, like so. So in order to apply the Yoneda lemma, we want to work out this Hom functor associated with this object. This is Hom star comma blank. Turns out to be equal to this object that has a state for every natural number, and update operation just winds on the number. We can see this because well, I mean, I suppose if we're being really technical about it, we can actually do any action we want on one of these. So anyway, I suppose if we're being really technical about it, we can do any action we want on these things, because what we're basically saying is that a kind of object in this category of dynamical systems is a set that has this iteratable function from itself to itself, but it suffices just to keep record of what happens when we do it once on itself, because of course we can think about being able to repeat it. So how can we see that Hom star blank is n to the sigma? Well, there's only one object in C, so the only thing we need to think about is, as far as sets go, from this function, how does it operate on objects? We just need to know how does it operate on star. What's Hom star star? Well, it is this set of arrows from star to star, which is sigma to the 0, sigma to the 1, sigma to the 2, and so on. So we associate those with the natural numbers 0, 1, 2, blah, blah, blah. And then Hom, pretty easy to see that Hom star sigma to the 1 operating on sigma to the n gives us sigma to the n plus 1. I mean, composition in this free monoid is commutative, so even though doing this action when we're inside the Hom functor is like sort of doing a left action on this, and also applying there's also this natural transformation from Hom star comma blank to Hom star comma blank, and that technically is composing on the right with h of sigma sigma or h of s, whatever you want to call it. But it doesn't matter because it's commutative. So these are basically very similar things. We can also consider the case where our generator has some restriction, like sigma to the alpha is sigma to the beta. And I think then we get a subcategory of sets of this category of dynamical systems. And I'm not sure if it can be expressed in terms of sets, this set dynamical system sliced over something. For example, can we somehow get the category of involutions, dynamical systems that correspond to involutions? Is it somehow related to this set of dynamical systems sliced over this category? Not sure. Anyway, hom star comma star is this set here, as I said. Doing a action using sigma to the power of I on this gives sigma power of n plus I. And we can apply the Yoneda lemma. So an element of I'm using some new notation before I talk about the Yoneda lemma in this context. Just let me introduce this new notation. So in general then, when we're thinking about presheaves, well, not presheaves because we're not using contravariant functors, but when we're thinking about these categories of functors into sets, for an element E of G of E, we write E arrow to denote the natural transformation that E corresponds with under this Yoneda isomorphism, this thing I've been calling epsilon. And on the other hand, we let epsilon dots be the E. So that's the element of G of E that this natural transformation corresponds with. So we use a dot to get from the natural transformation to the element, and we use an arrow to get from the element to the natural transformation. So then we can denote this result we have about doing actions and representing that in Yoneda language quite neatly. We have that get an element of G of E, turn it into a natural transformation, and do it after H of S, and you get the natural transformation that corresponds to doing the S action on E. So anyway, what's this look like in our category of dynamical systems? Well, remember we have hom star comma blank is n to the sigma. So critically, we end up with this, that if we're dealing with a, here we have a dynamical system, a to the power of alpha, and this will correspond to a sort of functor a from our monoid to set. And then if we have an element E I mean, really a state. We could, I mean, the technical thing we should probably say it's, we're talking about E of A of star, where we're considering A as a functor from C to set, and this update function alpha, A of sigma is really alpha. Okay. So the core thing we get out of all of this is that applying alpha n times to E is the same thing we get if we find the kind of natural transformation corresponding to E, which is coming out of the sort of counting dynamical system. So here, like if this is A and here's E, here's n to the s, then we're talking about this one here is blank, that's such that if it sends 0 here to E, okay, maybe I should say star, but there's only one component to these natural transformations anyway. But if we get this is how we get E arrow. This is this natural transformation from this counting dynamical system into A. Then if we see how this maps state n of our natural number dynamical system, then that'll give us what happens to E after we do n updates of it. 1, 2, 1, 2. So over here, under alpha, the update associated with n, and we can also write that like this. So we could say, to get this, we sort of take this thing and then we apply a couple of these wind-on updates. Well, H of S, but it's pretty similar to S. First. So, yeah, that's the idea. Now, that's the basic notion of, so I mean the bottom line of this is that states in a dynamical system correspond to arrows from this natural number object that sends 0 to that state. Now there's also this point now of, okay, what's the sub-object classifier of this category of dynamical systems? Well, a state of the sub-object classifier, a state x dot, will correspond to a natural transformation x from our counting dynamical system to omega, which would correspond to a sub-object of our counting dynamical system. So what are the sub-objects? Well, they're the sub-dynamical systems. So there's the empty one, the whole one, the one where we just take all the states from 1 onwards, the one where we take all the states from 2 onwards, the one where we take the states from 3 onwards, and so on. So we label these. The whole one we call 0, The one where we take state 1 we call 1, the one where we take 2 we call 2, and so on. And the empty one we call infinity. And the other thing is, okay, we have these states of entity S. And I mean, you know, when we're forming these sets, these are just elements. We can think of them as sort of labeled of anything that they're isomorphic to, really. So we can think of them as labeled like this. And but, you know, there's really this kind of correspondence going on. So we're going from states, using needed to go to natural transformations, and using the property of the subobject classifier, which is that for any monic, there's this unique classifying arrow such that that monic is the pullback of true along that classifying arrow, and so on. We're using that to convert, well, we're really just doing the pullback of true along this x here to get this x star. So x star represents the subobject classified by x. Okay, but then the other thing, of course, is how what do the actions do? Because we know that omega ought to be a dynamical system. So now we know it has these states 0, 1, 2, blah, 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 and infinity. But how does the update arrow work on omega? So the point is, in this language, we can think of the thing we get by updating this x dot with s. We can think of that as h of s to the -1 of x star. Okay, so h of s in this context, it's just essentially applying this update. So we can think that, for example, if we've got 2 here, that's all this stuff. And then if we just sort of pull that back along h of s, we're really after this kind of inverse image of that sub-object under x, which is going to be like this. Okay. So this is all the stuff that, if we apply s to this set of states, we get the blue set of states. And so we can think of this sort of omega to the s operation as going like this. And it'll leave the full set invariant and the empty set invariant. So you can pause the video on this if you want to see the argument more slowly developed. But the point is that the subobject classifier looks like this. True here corresponds to the full subobject I mean, each of these states here of omega, they correspond to a subobject of hom star comma blank. The full one corresponds to true, the empty one corresponds to false. This is usually the case. For example, this 2 here, like each of these states corresponds to a subobject of n. So 2, for example, corresponds to the subobject. 2 goes to 3, goes to 4, and so on. And then updating that using S is like pulling it back along H of S, which in this case gives us this sort of slightly bigger, which is 1 goes to 2, goes to 3, goes to 4. This slightly bigger subobject of n with update function S. And that's why the structure of omega is as it is. And this infinity corresponds to the empty subobject of the counting dynamical system, and this 0 corresponds to the full one, which is the true thing, where everything corresponds to true, and it all matches up very nicely. Yeah. So this makes sense as well, because 1 to the power of n is the pullback of true along this arrow, which sends all of n to 0, and that all makes sense. So this 0 here represents true, and for example, this this is showing how this state 1 here, if we have this arrow which is sending our dynamical system into that, it'll send all of this stuff after one update into this true thing, this fixed point here, this 0 on the left of omega. Okay, so now we're ready to start talking about some logic. Now we've actually built up this understanding of what sets, what the subobject classifier of this category of dynamical systems is like. So one thing we're going to need is, what does omega times omega look like? And we see it here. So, I mean, this is somewhat self-explanatory. The main point is that the product of dynamical systems A with update function alpha and B with update function beta, its set of states will be the Cartesian product of the set of states of A and the set of states of B, and such an element A comma B within that product, if we update it, it'll get updated to go to alpha of A comma beta of B. So to draw these things, you just draw copies of A and B down here, and then it's quite easy to fill in these. For example, we know that 2 updates to 1 and in A, and 3 updates to 2 in B, so 2, 3 updates to 1, 2 in A times B, so on. So we get this picture of omega times omega. Now we're basically starting to collect together these different logical operations. So one of them that we're interested in is this AND. So AND is the classifying arrow of true comma true. So I mean AND is so we think of it as a classifying arrow of this sub-object that I've circled in red. And it's going to be an arrow from omega times omega to omega. So the way it's going to work, it's going to send all of these things on a different connection component to this, to infinity. So anything with an infinity in gets sent to an infinity. 0, 0 gets sent to true, and all of these other states get sent to the number of updates you have to do in omega times omega to get to here, which is going to be the maximum entry. Okay, so for example, this here takes 3 updates, 1, 2, 3. So pretty simply, we can say that, because I mean, we can really label the states of omega with these integers 0, 1, 2, 3, etc., and infinity, and then we can just say that for any sort of things like that, so we'll just write this slightly sloppy notation for d and d dash in omega. So we're thinking of these as states now. We're going to have the AND working on d, and d dash is going to be the maximum of d and d dash. So of course, if either of these are infinity, then the output is infinity, corresponding to false. And we can see that the only way we get a 0 out of this, a true, is if d and d dash are both true. That would be like the thing belonging to both subdynamical systems. Now, of course, this AND operation corresponds to the intersection of 2 dynamical systems. So, for example, this extension here, like say we have sub-objects A and B of X, then we've got this extension of chi of A of X and chi of B of X for X in capital X is actually just going to be equal to A intersection B. And we can remember how we can get another way we can get intersections. We've got these 2 monics, A and B. If we do the pullback of one along the other, we get something else up here. And then this diagonal arrow, well, we can also think of being the intersection of A and B. That'll be a monic too. Yeah, quite a bit of this remaining video is trying to describe how different logical operations work in this category of dynamical systems. Now, usually I can directly drill down and say like how the sort of things work as mappings between, you know, omega, well, different powers of omega. But I mean, sometimes for like complicated stuff like for all and whatnot, it can be hard to do that. But you know, when you have a classifying arrow into omega, at least in the category of dynamical systems, I'm not sure how probably this works anyway. In fact, I'm pretty sure it does work in general, but certainly in the category of dynamical systems, if you just know, so say you have some sub-object. So okay, let's cook up a example. Well, I've got one here actually. Yeah, so we've got this dynamical system V, and we have some classifying arrow chi of A, which is an arrow from V to omega. Well, okay, if you know all about chi A, that's fine, but what about if you just know which states of V get sent to true under chi of A? Well, that's clearly enough to be able to find the sub-object A, because that is just the, essentially it's just a set of states that get sent to true, or 0 in our case, under chi of A. But like, what about if you want to know the values of chi for the other stuff? Well, it's pretty simple. In fact, this is how you really go from a sub-object A of V to this chi A. You can just define for a state X of V, we just define chi A of X to be the minimum n, such that you have to do n updates on V to get a member of this sub-object A. Okay, so, and then you'd put an infinity there if you never get in A. Okay. Now it seems to me that there's got to be an easier way to do this, but one way that you can get, so I mean there's a couple of interesting kinds of operations that that you can do. So if you've got a sub-dynamical system, so I mean, when I talk about the attractor of a dynamical system, I'm really talking about, so I mean, I'm usually talking about a finite dynamical system, and I'm talking about the cycle that it ends up in. I mean, it could be a sort of one cycle, if it's if it ends at a fixed point. In this case, it's a 4 cycle, so this square here would be the attractor. Now, it seems to me that you can get the attractor of a sub-dynamical system A. Although actually, I'm not sure. I think it would have to be a connected sub-dynamical system A in order for this to work. And there's a way we can check that. I'll have to come back to this.